All right, let's get right into it. We're talking about a project that gets to the very heart of one of AI's biggest problems, trust. I mean, how can you really trust an AI's prediction when we're talking about a multi-million-dollar jet engine and, the safety of everyone on board? That's where turbofan reason comes in. It's all about one simple, powerful idea, teaching a machine to actually show its work.
So, picture this. You're the maintenance chief for an airline. An alert flashes on your screen. It says a critical engine on one of your planes has just 15 flight cycles left before it fails. What do? Do you ground the plane right away, which costs a fortune? Or do you take a chance? Right now, that prediction, it's just a number. And that, right there, is the million-dollar question. The number by itself isn't enough, not even close. You've got to know why the AI thinks that. Which sensor is going haywire? What specific pattern of failure is it seeing? Without that why, the prediction is really just a well-educated guess.
This brings us to the core problem in aviation and so many other critical fields. It's what we call the AI black box. You feed data in one end, a prediction pops out the other, and what happens in the middle? Total mystery. In an industry where every single decision has to be justified, that's a huge wall to climb.
This really shows you the difference in a nutshell. A standard AI just hands you an answer from inside that mystery box. But turbofan reason wedges this crucial step right in the middle. A transparent, easy-to-understand reasoning process. The whole goal is to turn that black box into a glass box, building a bridge of trust between the person and the machine. So how on earth do you do it? How do you actually teach a language model to think like an engine mechanic? Well, the biggest challenge is that the main dataset from NASA, it's just a stream of numbers from sensors. There are no senses, no explanations, nothing. So the folks behind this project had to basically invent the textbook before they could teach the class. Okay, so here's the four-step plan they came up with. First, they take all that raw sensor data from NASA. Then, and this is the really clever part, they use a rule-based expert system they call the teacher to analyze that data. It's programmed to spot known failure signs. Step 3, the teacher then writes out a step-by-step diagnosis in plain English, creating the training data from scratch. And finally, they use all that text to fine-tune the Gemma language model, teaching it to connect the dots between raw numbers and expert reasoning. Now, let's talk about the engine behind the engine, so to speak. Pulling off a project this ambitious, especially on a tight hackathon deadline, means you need the absolute best tools for the job. And choosing Google's Tunix library, which is built on JAX, wasn't just a nice-to-have, it was totally necessary. Using Tunix and JAX gave them 3 huge advantages. First up, speed. In a hackathon where every minute counts, running on TPUs with JAX is an absolute game changer. It let them try things out and fine-tune the model way faster. Second, it's super flexible. Tunix made it way easier to build a custom pipeline to feed their made-up diagnostic text into the model. And third, it's future-proof. The whole setup is ready to go for more advanced stuff down the line, like reinforcement learning. So after all that work, creating the data, building the pipeline, the super fast training, what does the final result actually look like? This is where it all comes together. Let's check out what the fully trained model can do. And boom, there it is. This is that show your work moment we've been talking about. The model doesn't just spit out a number, it gives you this clean, structured diagnosis. See how it starts with the reasoning? It calls out specific sensors like the low-pressure turbine outlet temp and points out that the pressure is diverging. Only after it lays out all the evidence does it give you the final answer, a clear warning status and an estimated 72 cycles of remaining useful life. So what's the big picture here? What's the real impact of all this? Well, it's a huge shift in how we approach AI in these high-stakes situations. We're literally moving away from that mysterious black box and towards something we can actually look inside, a transparent glass box. The benefits here are just crystal clear. First, and this is the big one, is trust. A human operator can now read the AI's thinking, check it against their own expertise, and then make a call with real confidence. But here's the cool side effect. The accuracy actually gets better, too. By forcing the model to create this logical chain of thought, its final prediction becomes more stable and more reliable. And yet, this project was all about turbofans. But you can see how this idea could go so much further, right? Think about medical diagnoses or spotting financial fraud or managing a power grid. What we have here is a powerful blueprint for building explainable AI anywhere, that a prediction isn't just data, it's a decision with massive real-world consequences. The question is no longer just what does the AI think, but how did it get there?